what we're going to do with our findings from the mass spring system FET is come up with a justification for the expression that we said described how the period of a mass spring system behaves. But to describe the behavior of any kind of oscillating system, including a mass spring system, you have to have a driving or restoring force for the oscillation, and that's described by something called Hooke's law, which you were told during the initial breakdown of how the FET proceeded, is the expression F sub s equals negative k delta x. What that describes is something called the elastic force, where F sub s is the blue arrow in both diagrams, where the first diagram is a stretched spring, and the elastic force is trying to pull the mass back to that dashed equilibrium line of the spring. And in the third picture, that elastic force is also trying to push the mass back again to the equilibrium position of the string. So all the elastic force does is try to restore the spring to the shape it was in the very first picture, which is equilibrium. That elastic force, according to Hooke's law, depends on a K, which is something called the spring constant of the spring. It essentially tells you how strong or springy it is, if you want to use technical terms. But it also depends on that delta x, which is the direction of displacement of the end of the spring from that equilibrium position. So note that the negative in Hooke's law is describing the opposite direction that the elastic force points from that displacement. Now, with that in mind, we need to make sure we know how the rest of the behavior of the spring proceeds due to the action of this elastic force according to Hooke's law. Now, the oscillation generally looks like the mass bouncing up and down at the end of the spring as the spring contracts, extends, and tries to get back to equilibrium and generally misses it. That pattern of motion happens to be a wave, which you may be able to see if we overlay a progressing wave on a bouncing up and down particle that only moves vertically up and down. That wave, or any wave behavior for that matter, is described by this somewhat monster of an equation. This is called a second order differential equation, and specifically it is called the wave equation. Now, while this looks kind of nasty, it's actually not that bad for us. The solution to it is actually pretty nice. It just says that the position in the vertical x dimension for the end of the spring or any wave depends on a cosine wave. So we end up justifying that the wave equation above gives us some kind of a sinusoidal wave. And we can make this even easier because that whole second order differential equation business comes from the fact that d squared x over dt squared is just the linear acceleration that the end of the spring experiences as the mass spring system oscillates. What may be a little bit odd about this expression is that omega, because you're used to calling that omega angular velocity, but in this case this is called angular frequency, which is sort of related but not quite the exact same thing. So to make sense of what that is, first of all, recognize that you've probably heard the word frequency before, and it's related to the period. So if you want to see where the period is, the mass spring system is going to bounce up and down where the green arrows are showing the velocity of the mass spring system as it bobs up and down, but then the green circled parts are where there is zero velocity, which happens to be at the extremes of the motion of the mass spring system. The yellow arrows show the linear acceleration, which is going to be pointing back towards the equilibrium position at all points on there. If you look through the cycling of this progression, you can see that the first two pictures are a quarter period apart. That is a quarter of the way along the repetition of the cosine wave. And then when you get all the way up to the top, you have progressed through half a period, then 3/4 of a period when you're back at equilibrium, and finally the full period only occurs once it's back down at rest, experiencing the same upward acceleration. And therefore you would see a whole second period occur by that third trough along the wave. In general, whenever we talk about the relationship between when those peaks happen to when the period occurs, we have something called a cyclical frequency, or frequently just called frequency. That frequency is really just an inverse to the period, and what it's describing is how often that the wave pattern repeats per second, or how many revolutions you see per second. Now, in general, that seems like a pretty straightforward way to talk about any kind of oscillation, except for the problem that you may remember from angular motion, that revolutions are not a very easy unit to work with other units. And so instead of using revolutions as our main form of describing frequency, we instead switch to a more familiar term in angular quantities, and so we coin a new frequency called the angular frequency, and that frequency is measured in radians per second. The radian is still related to the revolution the same way it was in angular motion, and so a full revolution is 2 pi radians, meaning that omega depends on 2 pi over the period. So with all this in mind, we're going to use this definition of angular frequency to determine the period of the mass spring system, starting off with the wave equation as our fundamental justification. So the mass spring system has to follow a pattern where the linear acceleration of the mass at the end of the spring depends on the negative times the square of the angular frequency of the oscillation times the linear displacement of the spring from equilibrium. Now we can make a substitution because we know that that linear acceleration is caused by the elastic force according to Hooke's law, and so if we substitute those together, we can show that the elastic force is going to be directly related to that angular frequency and the mass will be inversely related. And then we can also plug in for the elastic force the expression for Hooke's law and come up with a somewhat more complicated looking equation to put these quantities together, but now we've got all the quantities that we know somehow or another either play a part or don't play a part in the oscillation of a mass spring system. So now that we've got everything put together, let's get rid of the negatives because they cancel, and it also turns out we can cancel the linear displacement, which agrees with our original findings from the FET that it actually doesn't matter how far you stretch or compress the mass spring system, it always oscillates with the same period, which means the oscillation pattern or the angular frequency of the mass spring system only depends on the spring constant and the mass. And so if we piece this together with the period as defined by the angular, as related to the angular frequency, make them both look like they are individual angular frequencies by taking square roots of the left equation, then we can piece the whole thing together and show this relationship between K, M, and T. And then if we just rearrange those terms by way of a proportion and cross multiplying, we have the period of a mass spring system being 2 pi times the root of M over K, or the period should be directly related to the square root of the mass and inversely related to the square root of the spring constant.